This tutorial will describe some of the basic properties of spiking chemical synapses. We'll begin this tutorial by creating a project and adding a new organism. Then open the behavioral editor and add 3 spiking neurons. Now add an excitatory synaptic connection between neurons 1 and 3 and select the nicotinic acetylcholine spiking chemical synapse. Spiking chemical synapses can be either excitatory or inhibitory. What determines this is the equilibrum potential. If the equilibrum potential is less negative than the membrane voltage, then it will allow positive current to flow into the cell to depolarize it. In this case, the equilibrium potential is set to negative 10 millivolts, while the resting potential of the neuron is set to negative 60 millivolts. If we look at the hyperpolarizing IPSP synapse type, then we can see that its equilibrium potential is set to negative 70 millivolts, which is lower than the resting potential and will cause inhibition when it's activated. Let's switch back to the nicotinic acetylcholine synapse and change its synaptic conductance to 1.5 microsiemens. This property controls the strength of the synaptic connection between the two neurons. Synaptic conductance is modeled in the following way. When the presynaptic neuron generates a spike, there is a user-defined delay between the occurrence of that spike and the postsynaptic effect. Once the delay is over, the conductance for this synapse is immediately changed to the value of its synaptic conductance parameter. The conductance value then slowly decays over time in an exponential manner that's controlled by the decay rate parameter. The longer the decay rate, the longer it takes for the conductance to go back to zero, and the more of an effect that synapse will have on the postsynaptic neuron. Now let's add an inhibitory synapse between neurons 2 and 3. Choose the hyperpolarizing IPSP synapse. Next, we need to add some stimuli. Add a tonic current stimulus to neuron 1. Set its start time to 40 milliseconds, end time to 140 milliseconds, and set its amplitude to 30 nanoamps. Let's also add a tonic stimulus to neuron 2. Set its start time to 160 milliseconds, end time to 260 milliseconds, and amplitude to 30 nanoamps. Now let's add a line chart so we can watch the membrane voltages of our neurons. Set its end time to 300 milliseconds, and select the collect data interval to 0.2 milliseconds. This is the time step used by this neural module, and it will allow us to see all the details of the simulation. Now let's run our simulation. We can see that when neuron 1 fired, it produced depolarization in neuron 3 that caused it to fire spikes, while neuron 2 firing caused hyperpolarization in neuron 3. Let's go and change the decay rate of our excitatory synapse. increasing the decay rate should increase the depolarizing effect on the neuron and lead to more robust firing in neuron 3. To see this more clearly, let's also disable neuron 2's stimulus. Now run the simulation, and we can see that neuron 3 did fire much more than the first time. Next, let's change the facilitation. Facilitation is an increase in the synaptic response following a spike. Spiking chemical synapses can be defined as facilitating or anti-facilitating, which leads to a decrease in the response strength. Facilitation is modeled in the following way. If a PSP occurs immediately following a PSP of the same type from the same presynaptic neuron, then the amplitude of the conductance increase at the start of the second PSP is the value of the conductance increase at the start of the first PSP multiplied by the relative facilitation factor. Therefore, a facilitation value of 1 means that no facilitation occurs. A value greater than 1 means the synaptic response increases, while a value less than 1 means the synaptic response decreases. As the time interval between the two synaptic events increases, the degree of facilitation decays back exponentially towards a value of 1 with the defined decay time constant. Let's decrease the relative facilitation to 0.5. This should lead to a reduction in the strength of the synaptic response. Run the simulation. This time we only get 2 measly spikes because of the anti-facilitation is so strong. Let's go back and change the facilitation to 2.5. This time we get a much stronger response than we initially had. Now let's go back and re-enable the stimulus to neuron 2 and rerun the simulation. We can see that once neuron 2 begins firing, it causes hyperpolarization in neuron 3, which begins terminating the response from neuron 1. This tutorial has demonstrated some of the basic principles of spiking chemical synapses and how to use them in your project.